let's consider this vector valued function, and the limit this time as t approaches positive infinity. Okay, so let's consider the component functions. Now, what do you think the limit should be in this case? Well, the limit of the last one's probably this vector, the component here is easiest to evaluate. What's the limit of e to the minus t going to be as t goes to infinity? 0, right? So it's just the other two that we want to evaluate. So what do you think the limits of the other two are going to be? 0. Why? Yes. Yeah. Yes. And so that's sort of like the intuitive, like that's what's going on in our heads. But can you sort of give us some sort of theorem or proper technique? So you're right, but any ideas on how you might prove it or justify it, perhaps? No? Anyone? Anyone want to step in? Yeah, who said that? Yes, you will too. Pinching theorem or the squeeze theorem or the sandwich theorem, depending on where you are in the world. So I'm just going to restrict the domain to, oh, hang on. Sorry, let me cover that up. Sine squared is between 0 and 1. If you divide, then you can have that, right? So the pinching theorem or the sandwich theorem or the squeeze theorem, whatever you want to call it, says we can take limits, keep the inequalities, and if those, if we get equality, then we can say that the limit's going to be 0. So you put a limit here, a limit here, a limit here, limit here, limit here, limit here. On the right-hand side, you're going to get 0. So the thing in the middle has got to be greater than or equal to 0 and less than or equal to 0. Well, it's got to be 0 then. Sandwich. So we know the limit of this is going to be 0 as well. Okay. So again, this is just an illustration of applying first-year techniques to the individual component functions. So you can do that. That's an important thing to recognise.